on this computer. Hi, everyone. My name is Matthew Holmes, and presenting with me today is Sean Even. We are both mechanical engineers, and we work together on the Modular Oceanic AUV for Novel Actuation, or the MOANA project. Our ocean hosts the beginning of all life on our planet, and it is still home to the vast majority of it today. It provides us with more than half of the air we breathe, and it is critical for climate regulation, food, and our way of life as we know it. Here at Santa Clara University, the Robotic Systems Laboratory, or RSL, has spent decades creating a robotic fleet to aid efforts to better understand our ocean. At this time, the lab has several tethered and surface vehicles, but nothing capable of exploring at great depths for long periods of time. Through this project, our senior design team created a test vehicle for the RSL to demonstrate the feasibility of low-power internal actuation for a long-range autonomous underwater vehicle, or AUV. Our test vehicle not only proves the capabilities of long-range and long-endurance technology, but has provided the RSL with a foundational prototype for an eventual production system. As shown in the diagram in the middle of the screen, at a bare minimum, our vehicle needed to be able to be conveniently transported to and deployed from a shore or boat test environment. Next, the vehicle needed to be able to travel and dive to a suitable depth for operations. From there, it would perform operations at a desired area of interest, and finally, the vehicle would return to its deployment location for recovery. On the right, we have pictured a high-level overview of the layout of our vehicle. Inside of the rigid cylindrical hull, the control and navigation, depth control, and pitch control subsystems are housed in watertight enclosures. These are connected together via cables that stem from the battery pack housed in the pitch control enclosure. The nose and tail cones are attached to either end of the vehicle, with the tail cone housing the yaw control and the propulsion subsystems. From nose to tail, the vehicle is approximately 8 feet long with a 1 foot diameter.
Next, we'll dive into the specific subsystems that make up the MOANA. For convenience, we split these subsystems into 3 categories: the hull, the computational subsystems, and the control subsystems. The hull of the vehicle is designed with a rail at the bottom to support subsystem modularity, and several hatches were cut into the cylindrical surface. The top hatch allows for internal visibility and ease of access for benchtop and field testing, while the bottom 2 act as water dump hatches to make the vehicle easy to recover. Interfacing with the external hull are 3D printed nose and tail cones. The shapes of these features were optimized using known hydrodynamic properties and finite element analysis. In terms of computational systems, the team developed a CAN bus, a power bus, and a mission control computer. The CAN network is a series of microcontrollers which interact with sensors and motors in each subsystem to operate the MOANA. The power bus breaks up energy stored in the battery and delivers an adequate amount to each subsystem. Finally, the mission control computer, or MCC, is the brain of the MOANA. It commands all the other subsystems and interfaces with the laptop to control our AUV in the field. Finally, the control subsystems consisted of pitch, depth, yaw, and thrust control. The pitch of the vehicle was controlled with the movement of our vehicle's battery on a mass slider. The depth was controlled by drawing in or expelling water from syringes within the depth control enclosure. The yaw control subsystem turns the MOANA in the horizontal plane through the use of motor-driven flaps at the back of the vehicle. Finally, the thruster is an off-the-shelf propeller that propels the vehicle forward. After a year of design, the team was able to conduct a surface test after fabrication was completed. Here's what we achieved with our first in-water test. First, we demonstrated the use of CAN and remote communication while the vehicle was on the surface. Second, we tested our propulsion system at 20% power and observed forward acceleration of the MOANA. Unfortunately, the pitch control subsystem was not tested in water due to unknown factors, but was proven during on-land benchtop testing. There is much more work and testing to be done on the MOANA to reach full functionality in the ocean. And we are excited to pass the baton onto future teams who will help finish the vehicle and ultimately better understand our oceans. Thanks for joining us.